Okay, thank you, Pedro. Hey, good morning, everyone. So my name is PeiYu Cai from University of Edinburgh, and today I'll be discussing the magnetization reversal in van der Waals ferromagnet iron germanium telluride 312. We collaborated this project with Argonne National Lab and University of Arkansas, and we found out that beyond the standard stripe to skyrmion transition, field cooling stabilizes a novel reversal pathway. My macromagnetic simulations will demonstrate that the new path is topologically protected, which preserves the system's topological charge in a network of 360-degree domain walls, and hence the name suggested. So the van der Waals material FGT is well known for establishing skyrmions. However, the detailed nanos reversal dynamics and especially the influence of magnetic history remain largely unexplored. So this leads to our key question that how does the field cooling history alter the reversal pathway and the stability of the topological charge? To study this, we used a in situ cryo-Lorentz transmission electron microscope, or LTEM, on a single exfoliated FGT flake. So by using the single flake approach, where thicknesses varies from 23 nanometers in the top right region and to 97 nanometer in the bottom region, it is very critical for our measurements because it allows us to isolate the effects of thicknesses without the complication of a sample-to-sample variability because everything is measured on the same sample. This image on the right that shows the LTEM resolved in focus on the top and the autofocus magnetization profiles of a small field code sample. And the difference between the in-focus and autofocus LTEM resolution suggested that this magnetization structure that we see is a neo-type structure. Experimentally, we observed the two vastly different reversal mechanisms, which on the top row shows a zero field cooling path. At Raman's, we see stripes forming, and as we apply a negative field, the stripe that contract into skyrmions, for example, at this spot, and then which they are annihilated at higher fields. So this pathway indicated a topological charge annihilation because the topological charge that is start with 0 and it ends with 0. In the middle, they are not 0. And in sharp contrast, the bottom row shows the field cooling path. So we first field cooling at 300 gauss to see a dense skyrmion lattice. And as we route the field and then apply a negative field, the skyrmions, they do not annihilate. However, they expand and they emerge into larger grains, which forms this novel facelet patch face that we observe here. So my simulations reveal that the driving force for this merger is that the skyrmion cores are already aligned with the reverse field, so that they are already in a low energy state. However, the system can further drop the total energy even further by expanding this cores, such that the more cores will align towards the applied field. In this way, they reduce the total Zima, they reduce the Zima energy, so that the Zima energy will be the primary force for compelling this transition and the emerging of the skyrmion bubbles. But now the critical question is that what is this new patch phase that we see here, and why is it so stable to exist at just to be able to stand at higher fields, say as compared to the zero field cooling phase? So to understand the physics of this phase, I constructed a system with micromagnetic simulation package MUMAX3, and the simulation parameters that were drawn either from experimental parameters such as the anisotropy, first order uniaxial anisotropy constant, and the saturation magnetization, or there were some literature reported values that were taken, for example, the exchange stiffness or and a DMI interaction strength. Everything is in SI units, and we have constructed a simulation at 400 Kelvin using a normalized temperature function. We used a cell size of 5 nanometer across all dimensions, which is less than the 12 nanometer exchange length. the entire simulated area is 200, just 2 micron by 2 micron in lateral size to make sure it matches with the size of the experiment. And now you will see that we have used a 500 Gauss simulation field, which is a bit higher than the 300 Gauss experimental field, to stabilize the Skyrmion phase. This is actually not a flaw because our sensitivity analysis confirmed that this is actually expected. So the Skyrmion lattice is a delicate energy balance between multiple interactions, and in a way that if we have a minor reduction or deviation of the saturation magnetization, or DMI, of this specific exfoliated flake, which could come from from sample to sample differences, which they would require a higher, stronger external Zeeman energy to compensate and stabilize the same state, which therefore it would need a higher field as we have used here, and the rest parameters from literature. So this is our simulated results of a magnetic reversal from field called Skyrmion nucleation into patches and then finally to ferromagnet state. We consider a system consisting of a 45 nanometer thickness at the top and a 75 nanometer thickness at the bottom. So just like the experiments, we field code a sample from random magnetization to nucleate the skyrmions at 300 Gauss or 500 Gauss for simulation. And then we moved the field to 0 Gauss and gradually applied an anti-parallel field with increasing strength. And then we can observe the evolution of the skyrmions, which we can see that the simulation closely reproduces the experimental patch network that we observe here, for example, in this state. So that So now we have this is a video demonstration of a simulated magnetic reversal, and I'll play this video to show the dynamics of the reversal. Yeah, and then we stop the field at 3,000 Gauss or negative 3 Tesla when nothing has changed after that. We can see that the reversal process matches very well with the experimental observations, so which now we can investigate more based on that. Because we have this validated model, this allows us to see what LTEM or Lorentz transmission electron microscope cannot show, which is the underlying spin texture. So this slide is a definitive proof which shows the patch phase in a network of 360-degree domain walls. We first extracted the spin profile from a skyrmion phase. We first extracted the spin profile from a skyrmion phase, and we numerically confirmed that the initial skyrmions have a topological charge of K equals to -1, which proves its non-trivial topological configuration as a skyrmion. And after merging into patches on the applied field, the sharp peaks of the in-plane MX component clearly shows a full 360-degree rotation, as indicated here. And then this confirms that these walls are the topological remnants of a Neal-type skyrmion merger. So essentially, we combine this and this in order to form this. So these are remnants of the skyrmion on the left. And now we have proven that what the phase is, we can use a simulation as an analytical tool to understand why it behaves in this way. So first, why do the domains paint so strongly at the step edges, as you can see in the experimental image here? So we extracted the energy density map from simulation, which provides the quantitative answer. Among all the energy density maps, we see that the demagnetization map has the highest contrast gradient precisely at the step between the two different thicknesses. This indicates an intense local straight field between the two regions of different thicknesses, and because it creates a significant energy barrier that prevents the domain wall motion from crossing each other, which identifies the local demagnetization effect as a dominant driving force for the observed panning that we observe also here. And secondly, why is the patch phase more stable in thicker films, as shown in the experimental phase diagram, which we can see that as thickness increases, the greenish area indicated by the patch phase are much larger than in thin systems. So to answer this, I performed a systematic simulations of samples with varying thicknesses from 25 up to 250 nanometers. The relaxed energy density results showed a strong competition between interactions, and both the destabilizing demagnetization energy shown here and the stabilizing anisotropy energy shown here are maximal in the thinnest films shown in the red. However, as the film gets thicker, the demagnetization energy penalty decreases much rapidly and much more significantly than the stabilizing anisotropy energy, leading to a progressively lower total energy that we see in the top left plot. So this means that the system is more stable in the thicker system, even in the presence of a non-trivial spin configurations. The dominant reduction of this primary destabilizing force is the key factor that allows chiral texture to remain stable. This provides a fundamental basis for the critical thicknesses that we observe. So this brings us to the topological argument. The zero field cooling path is a topological annihilation, where stripes they start with trivial configuration, q equals 0, to skyrmions, and then back to a uniform state. But the field cooling is we call this a topological preservation, where we start with a skyrmion lattice, non-trivial, and we evolve to the patch network, also non-trivial. The topological chart is therefore conserved and redistributed into the 360-degree domain walls, which themselves are known to carry topological charge. So this finding is technologically relevant for domain wall memory applications, because 360-degree domain walls, which drive fields may cancel, are theoretically predicted to lack Walker breakdown phenomena. This could enable much higher domain wall velocities, which is a critical goal that we want to have in spintronic. So in conclusion, first we identify two distinct reversal pathways in Fe3GeTe2, topological annihilation and topological preservation. And second, my macromagnetic simulations prove the novel patch phase is a network of 360-degree domain walls, and confirming Q equals -1, which correspond to Néel-type skyrmions. Further, most importantly, the simulation revealed the key energetic mechanism, where the pinning at steps is driven by local demagnetization fields, and the intrinsic stability for thicker film is driven by the global reduction of demagnetization energy. So this work identifies a new topological protective reversal mechanism in van der Waals magnet and implications for topological spintronics. So I'd like to thank my collaborators and my funding resources, and thank you all for your attention. I'll be happy to take any questions.
Thank you, PeiYu. So we have a question from Maud. Maud, you can ask.
Thanks, Andre. Thank you, Pei, for the nice presentation. I have mainly three questions. The first is related to the slide where you show the energy densities.
Yeah.
So you basically have a system with a change in thickness, and it's like you assume, I don't know how you define the anisotropy in your simulations. Is there any interface anisotropy that is divided by the thickness itself, or you just define a uniaxial one?
We have used the uniaxial anisotropy.
So then the argument of saying that only Dmag energy is responsible in the effect between the two between the two parts with different anisotropies is maybe not exactly what happens in the experiment, because the anisotropy is also supposed to change in the case where you have these changes of thickness.
Yeah, that's true. But we have found that at least in simulations at the end, anisotropy energy to change is not as much as the demagnetization energy. So we have said that the demagnetization energy is what's suggested to be the dominant factor.
Okay.
Dominant factor that causes the transition.
Okay, I understand this. So the second question is related to the temperature itself. I didn't understood how you are modeling temperature in your case, because you said that we use some function to include the temperature effect.
So we have, yeah, that's a good question. So we have used 4 Kelvin temperature. So Max3 is modeled as a random noise with a normal distribution. So we have used 4 Kelvin. This is just an input parameter as a,
So you are basically augmenting energy with the Langevin thermal.
Yeah.
Do you consider, because in experiments, compared to modeling, there is one issue is that the Langevin thermostats are not describing what happens correctly in ferromagnets at low temperatures. So I don't know what is exactly the Curie temperature of your system, but if you are modeling something lower than Curie temperature, for sure there is a small shift between the experimental temperature and the one that you are considering in simulations. Do you have any comments about this, like discrepancy between the values where the phenomena that can take place in the experiment and compared to what you have in the simulation?
Yeah, so we have constructed the simulations at 4 Kelvin, and the experiment is also conducted at a very low temperature. And then the current temperature for this material is 200 Kelvin. So if we compare 4 Kelvin to 200 Kelvin, it's vastly different. So we do not consider the temperature effect will be very prominent in our simulations. And the topological temperature, which, the highest temperature, the topological objects they can exist, is also quite high compared to 4 Kelvin. So in our simulation, at least, and in this particular system, we do not think the temperature will play a very important role here because temperature is low.
Sorry, I also hear that I thought it was 400 Kelvin.
No, 4 Kelvin. Sorry, 4 Kelvin. Yeah.